to BKW Physics. I'm Mr. McCodley, and today we're going to talk about electric current. And basically the definition of electric current, as you see on the board, is the flow of electrons across a potential difference. And I want to relate it in your mind to a stream. Because if you look at a stream flowing by, or a creek flowing by your house, or whatever, the water flows, and we say, oh, that's the current. And I want you to think of electricity in kind of the same way. The thing that's flowing are the electrons. The electrons are flowing along, and what are they flowing in? They're not flowing in a creek bed, they're flowing in a conductor, wire, piece of metal. They can also flow through other things. They can flow through water, they can flow through your skin. But most of the time when we're thinking of electric current, we're thinking of it flowing through a conductor, some sort of wire. And what actually makes the electrons want to move is the potential difference. So we already talked about potential. And potential was kind of like this idea of the push. Okay? It was a push. And we drew some pictures previously for that. Without potential, the electrons don't go anywhere. They have no reason to. Once you provide the push, then they actually want to flow, and then you get current. Okay? So what are the things that provide the push? Let's make a quick list of examples of things that can provide a push. Where do you get potential from? Well, the first one I'll start you off is with a battery. What do you got for another one? Yes. Capacitor. We've been talking most recently about static. So we have static electricity, and we talked about how that builds up and then you get a potential. So these are some examples of sources of potential. And the one you use the most nowadays is batteries. Every device you use, your automobile, your phones, your any sort of computers, they all have these batteries in them. And the batteries are what provides the push to move the electrons. The electrons flow, which is called current, and then work is done, and we'll talk more about that later. But moving on to a more physics-y type of equation. If you look in your reference table, you will find that it says I is Q over T in the electrical section. And it's kind of a strange equation because remember from previous equations, Q means charge, and charge is in coulombs. T is still time, time is in seconds. And I, like what could I possibly be? Well, I unfortunately means current. Okay? It doesn't make a lot of sense to people, but I is current. And current can be coulombs per second, sure, and you'll get it right on the regents if you do it that way. However, no one that knows anything about current calls it coulombs per second. They usually say, oh, that's an ampere, or an amp. And we abbreviate it with a capital A. So usually when you talk about current in physics, you say amps of current, and the abbreviation is capital A. So you have a certain number of amps of current, and to measure this, we use an ammeter. Now that's not I wrote it down specifically because it's not an amp meter, it's an ammeter. Okay, it's an ammeter. Ammeters measure the flow of electrons. Back up here real quick, what measures potential difference? What's that device called? Anyone know that? It's actually called a voltmeter. So in our next lesson we'll talk about ammeters and voltmeters, and I'll show you an example of how they work. But for now it's good enough to know that voltmeters will measure potential, ammeters will measure current. Let's move on to one more thing here. If you recall, potential was work over charge. I'm going to rearrange that and make it work is potential times charge. And if you also back up in your memory banks, you remember that power was work over time. Well, if I combine the two, if I take this and I plug it in here, I'm going to get power is potential times charge over time. And now, from what you've learned a moment ago, what is charge over time equal to? Less current. So this term right here can actually be just current. The reason I bring this up is because this is our main equation for finding the power in an electrical system. If you take the potential in volts and you multiply it by the current in amps, you will find the power. Now, in the American system, we usually say, cars have horsepower, or your lawnmower has horsepower. They talk about the horsepower of things. Well, that's not the normal units for when we're talking about the standard international system. And some of you are saying, oh, it must be a volt times an amp. Well, not exactly either. Power is actually in watts. And watts are abbreviated with a W. So, that should ring a bell, because when you look at light bulbs, a lot of times they will say the number of watts on them, and that's because they're telling you the power of that particular light bulb, okay? The power usage of that particular light bulb. So for today, physics.